Albert Einstein, Theory of Relativism.
Albert Einstein was born in Germany on March 1879. 6 weeks later, the family moved to Munich, where he later on began his schooling at the Leopold Gymnasium. Later, they moved to Italy and Albert continued his education at Aarau, Switzerland, and in 1896 he entered the Swiss Federal Polytechnic School in Zurich to be trained as a teacher in physics and mathematics. In 1901, the year he gained his diploma, he acquired Swiss citizenship, and as he was unable to find a teaching post, he accepted a position as technical assistant in the Swiss Patent Office. In 1905, he obtained his doctor's degree. Albert Einstein had a passion for inquiry that eventually led him to develop the special and general theories of relativity. In 1921, he won the Nobel Prize for Physics for his explanation of the photoelectric effect and immigrated to the US in the following decade after being targeted by the Nazis. Einstein is generally considered the most influential physicist of the 20th century, with his work also having a major impact on the development of atomic energy, with a focus on unified field theory during his later years. Einstein died on April 1955 in Princeton, New Jersey.
Relativity is just a method for two people to agree on what they see if one of them is moving. And since we all move about pretty regularly, we can find many examples of how useful relativity is in everyday life. One miracle of modern life is the Global Positioning System, or GPS. It is pretty amazing that the GPS can pinpoint your location anywhere on Earth to within a few yards. And this magic depends entirely on the existence of 24 satellites 12,000 miles above the Earth. Let's see some common experiences. If you are traveling in a car on a smooth straight stretch of highway, there's no sensation of motion at all. Looking at the phone or pouring a drink, everything looks and feels the same as if the car was sitting still. That's because relative to the car, you, the phone, and the drink are not moving. Note that this works only if the car not changing direction or speed. And if you want to know what it feels like to move 1,000 miles per hour, just look around, because if the earth spin, we zip along our time zone at a speed of 1,000 miles per hour. And because of its motion around the sun, the earth carries us through space about 67,000 miles per hour. And because of the motion of our solar system about the center of our galaxy, we are moving at more than 500,000 miles an hour. But it's not enough to ask how fast am I moving. We must ask how fast am I moving relative to some other thing. Let's make up a simple rule that allows two observers to agree on how fast something is moving. We begin at a moving escalator at the shopping complex. The escalator is moving at 3 miles per hour. So, if Farid simply stands on the escalator, he is moving at 3 miles per hour, relative to Khairi, who is standing still but not on the escalator. If Farid walks on the escalator at 3 miles per hour, he can accurately say he is walking 3 miles per hour, but Khairi sees Farid moving at 6 miles per hour. And if Farid walks against the escalator at 3 miles per hour, he can still say he is walking at 3 miles per hour, but now Khairi sees he is standing still, 0 miles per hour. So our first conclusion is that two observers can simply add or subtract their speed with respect to each other to any measurement of velocity they make. This idea is the basis of classical relativity. Here is the another scenario. Supposedly motorcycle moving down the road at a constant speed at 20 miles per hour. On the motorcycle, there are a passenger with a ball. As long as the motorcycle doesn't speed up or slow down, he can throw the ball up and down just the same as he would on the field. And when he throws the ball at 10 miles per hour, the ball indeed moving 10 miles per hour relative to him, rider and the motorcycle. But suppose an observer standing by the side of the road see the speed of that same ball. What do you guess the speed with observer measure for the ball? Well, the ball would already be moving at 20 miles per hour as the speed of the motorcycle. So this observer would measure a speed over 30 miles per hour for the throwing ball, the speed of the ball relative to the motorcycle plus the speed of the motorcycle relative to the observer. The example of adding velocities in the ball play an example is classical relativity at its finest.